Okay, take a stab at this question.
I can't do it that well. I see the concept.
Okay. Correct answer is
I think it's a wheelchair. It's a wheelchair.
correct answer is E. Correct answer is E. You have to go from a high index refraction to a low All right. So I'm going to demonstrate that. So I'll do it for this half first. So when going from a higher index of refraction like water into a lower index of refraction like air, bending away from the normal line, we see this. Good with that? Now, as we get closer, as we make the angle of angle of incidence greater, that refracted ray is getting closer and closer to the surface of the water. Point at which it goes parallel to the water. Okay, I don't care about that one. That's reflecting off the glass. The point at which it goes parallel to the water, that is the this angle here that makes that happen is the critical angle. Okay. If we go beyond that, then it experiences total internal reflection. Okay. So I want you to, so right here, some of it's reflected. See that? Okay. Watch what happens to the intensity, the brightness of that reflected angle when I exceed the critical angle. Okay, it gets brighter. That we've reached total internal reflection. None of it's getting out. Okay. For you all over here. Sorry, video people, you're just out of luck. All right, so here we see the rays coming out. as we increase the angle of incidence, this refracted ray gets closer and closer to the parallel of the surface of the water. When it reaches that, that's the critical angle. Critical angle is here. If we go past the critical angle, none of it gets out. All of it's reflected back in. So here, some of it's reflected, some of it's refracted. Okay. If we go beyond that, do you see how the intensity, the brightness of that gets brighter? Reflected red. Yes, no. Sure, Mr. Smiley, you just keep doing that thing with the laser. Okay, here comes the screen. Here comes the rest of the lights. Okay, so here, just trying to do that same thing. When the laser goes parallel to the surface, the angle that made this happen, this is the critical angle. Okay. And if we go beyond the critical angle, none of it's getting out, all of it's reflected back in. That's total internal reflection. Got that? Okay. So if we're asked to find what is the critical angle between glass and water, so this is just an application of Snell's law. Special case scenario. Okay. When you reach the critical angle, what do we always measure light angles from? From the normal. What is the angle? What is theta 2? 0 or 90? Here it is 90. Theta 2 is 90 degrees. This is our critical angle. Okay. As referenced here, you only get a critical angle when going from a high to a low index of refraction. So make sure that you put the higher of the two as N1. Okay. So when finding the critical angle, theta 2 is 90 degrees. That's the special case. Okay. Make sure you make N1 greater than N2 for the critical angle. And then you just solve for it. So that's what we're going for. Sine of 90 is what? 1. Easy peasy. So you get 0.875. Inverse sine, find that to be 61 degrees. Okay. Let's pretend that you messed this up and you put 1.33 here and 1.52 here. When you do the math, that's going to be greater than 1. When you go to do the inverse sine something greater than 1, calculator's not gonna like it. Like, error. Like, oh yeah. Oh, I should probably flip those. Yep, you should. So there's some user friendliness there. Good? Okay. So that's a photograph of what I was trying to show you. Total internal reflection. So video people, there you go. That's what everybody else saw. You don't have that, sorry. Print it off the slides. Have a conversation.
It's the first thing in the morning.
Tell your neighbor what you think. Did you already do that? What do you think? Okay, so for red, if this guy is a critical angle, everything that's beyond that, that's greater, your incident angle is greater than that, because we're always measuring from the normal line, is going to experience total internal reflection. Okay? So B, A and B. Okay? So the green one, some of it's going to be reflecting, some of it's going to be refracting. Okay? Obeying the law of reflection, and then Snell's law. Red, some of this is refracting, some of it is reflecting. The blue one, B, it's beyond the critical angle, so all of it is reflecting. Same thing with the purple. All of it is reflecting. None of it gets out. You get total internal reflection. Here's that. Okay. This one also is not on your packet. Right?
You can be more creative. Like it was 30 and 90, and that was like. Yeah, 45.
What do you say? Correct answer is A. Okay, we have a small critical angle. So going back to this one, let's say, okay, so here, the critical angle for this original one was 45 degrees. And the blue and the purple experienced total internal reflection. Let's say the green was the critical angle. That means the red, the blue, and the purple would all experience total internal reflection. There'd be more opportunity for total internal reflection to occur. Okay? So here, if this is the small critical angle, you got all this that could do total internal reflection. Okay? So what combination would give you a small critical angle? Tell your neighbor. Conversation about this question.
Yeah. As long as it could be D.
It's a B or D. That's what I heard.
How's it D? Why might it be? I don't know, I'm just going off of it. Just the small circle and those ones. So the vertical would go through.
Oh, wait. Yeah.
That would be point 19.
Correct answer is,
D.
survey says D, where you have the biggest contrast, biggest difference in the indices of refraction. You get the most bending here. You all right with that? So, one application of this is why diamonds are so cool looking. So diamond has a really high index of refraction, 2.42. When we compare that to air, the index or the angle of refraction is like, sorry, the critical angle is like, I'm making this up, I think 25 degrees or something. It's a crazy amount. So if you can cut the diamond correctly, what this is going to do is it's going to allow light to come in from all angles. But when light tries to get out of the back, it experiences total internal reflection, until it reaches the top. And so if you ever look at a engagement ring, the diamond is elevated, allowing light to come in all ways, but it only allows light to get out of the top. That's what makes the diamond look so brilliant. It actually takes optically all the light going in and only allows it to come out the light. So you're like, look at this. Okay, like you're only seeing the light that's coming out from all areas. Good with that? Now, that's coupled with the fact you have to cut it correctly, because if you don't cut it correctly, it'll still get out the back. But, yeah, good with that? Okay. Another application of this is fiber optics. Fiber optic is a type of plastic that has a really high index of refraction, not as high as diamond, but it is pretty high. So I'm going to shine the laser, just like it's demonstrated here. I'm going to shine a laser through here, and you can see, don't get mesmerized by the end here, but like look at the light inside the tube. This acts like a pipe for light. It's experiencing total internal reflection. It bounces off the sides until it reaches the end. And it's really bright. Bouncing around.
Let's see.
So, another application, or like a application of fiber optics, one application is Christmas decorations. All these clear strands are fiber optic cable. And if I pass if I shine the laser through here, so these are just the ends of this. I shine that through here. It's allowing the light to be piped through, and then once it hits the end, it comes out. Cool with that? Okay. And you can do some cool stuff with it. Like if you shine different colors through. Well, that. Okay. So the more practical application would be fiber optic cable. Metronet, Titmont, that type of stuff. Okay, so fiber optic cables going around, being installed around in our community, say the past 5 years, sorry. So passing information is really important for our society. Okay. Back when we were constrained to just like wires, we'd pass information through alternating current. Just different fluctuations of that. We need something binary, something for ones and zeros. For light, you can communicate that by turning the light on and off. Kind of like Morse code, but just flashes of light. you can pass that through fiber optic cable. Okay, so when they were installing fiber optic cable near my house, I went out and talked to the technician and told him I was a physics teacher. Like, so we geeked out a little bit on this. But this is a section of fiber optic cable that they're installing. You're gonna get a copper wire for like ground wire. Then you've got strength for, there's some fiberglass rods that are for strength, and then the middle part is the fiber optic cable part. And inside that white sleeve, there's like, I don't know, 10 of these strands, but each of these little itty bitty strands, he said, can carry data for 10 houses. So, pass that around. So, remember how we were talking about yesterday from the fish's point of view? Okay, so here, this is what this girl sees, is this girl's head like way up here. But around here, around this is actually the reflection from the sand experiencing total internal reflection going back in. Okay, so taking photographs underneath the water, the top of the water acts like a mirror because of total internal reflection. Okay, and this is actually my favorite picture. So inside of a hotel swimming pool, here's the guard, or the banister, and then it looks like it jumps all the way up to here, but really it's just continuing on. It just looks like it's a lot higher. And this is just a mirrored reflection of that. And then inside a swimming pool, like underneath, that's pretty cool. Do that. All right. Show me. Okay, so we're going from air to glass, back into air. Okay. Show me with your arm the normal line. What is that? Where is that going to be? Perpendicular to the surface. Rub, and is that going to bend away towards the normal line? Going from air to glass. It's going to bend towards the normal line. So here's no refraction. It's going to bend towards the normal line. You okay with that? And then when it gets to here, is it going to bend away or towards the normal line? Sorry, show me the normal line on this one. Again, like that. It's going to bend away or towards the normal line. Bend away from the normal line. I'm going to try to draw that better. I bent that pretty bad. Going to bend away from the normal line. Now, if this side and this side are parallel, then this ray and this ray are going to be parallel. So if your eyeball is over here, looking at it, you think you see the object over here. Shifted ever so slightly, depending on your angle and how thick the glass is. So that's why you can go to like the dentist or the doctor's office and they have an aquarium, and you can look at the corner of the aquarium and see a fish, the same fish in two different locations. Okay? And that's why you can get this thing going on. Good with that? Okay. What happens happens if we take it through a prism? The recommendation here would be to take it side by side, like take it each side separate. Tell your neighbor. Okay, ready? You ever have a guess? Find out. Show me the normal line for this first face. I want it perpendicular to this surface. Does that make sense? Okay. Here's no refraction. Straight through. What is it going to do? Bend away or towards the normal line? It's going to bend towards the normal line. So this would be towards, this would be away. It's going to bend towards the normal line. You okay with that? Show me the normal line for this next surface. Perpendicular. Here's no refraction. What's it going to do? Bend away towards the normal line. Away. Here's towards, here's away. How do we do? Correct answer is D. You see how I did that? Side by side. Okay. Now, you see how much refraction's going on there? If you make white light experience a lot of refraction, it actually separates out into the colors, the color spectrum. This is known as dispersion. Okay. And red light refracts the least. Purple and violet light refracts the most. The shorter the wavelength, the more it interacts and the slower it goes. So the more it bends. Good with that? So if you're following along in your notes, what is dispersion? When white light goes, separate out to the color spectrum. When does that occur? When there's a lot of refraction. The least angle is red. The greatest angle of deviation is purple and violet. Okay. Where do we see that? In rainbows. Okay. So, For a rainbow to occur, you need rain, sunlight, and your eyeballs. Okay? So white light comes in, refracts, most of it gets out, goes through it, but some of it's reflected back in. And then it refracts again. This is the part that makes the rainbow. If someone did this with a water drop with a laser, went through, most of it gets out, but some of it's reflected back in. This is the part that turns the rainbow. Okay? So, every water droplet spits out an entire color spectrum. But we only see the part that is shooting light into our eye. Okay? This raindrop is shooting the whole spectrum, but we only see red from this one. Purple is going over our head. So we see red up top. This one's shooting red, that hits our chest. But the purple gets to our eyes, so we see purple here. We have a whole color spectrum. Because it's a spherical raindrop, we see actually a cone. But it looks like a bow. Okay. So, what conditions you need? Well, you need the rain, the sun come out. You need to put your back towards the sun. Look away from the sun to see a rainbow. Okay. When is that going to happen? It only happens at a certain angle. It's when the sun is near the horizon, in the morning or in the evening. Okay. At noon, the only time you're going to get a rainbow is if you use a garden hose or sprinkler, and you can see it underneath you because the sun's at your back. Okay. So, so here's that cone. As you walk closer, you're receiving colors from different raindrops. So like finding a pot of gold at the end of the rainbow. Sucker. You're gonna get there. It moves with you. Not only that, rainbows are complete circles. The end of the circle. Okay, the land just cuts it off. Okay, but really it's a whole circle. Okay. Double rainbows occur when there's a whole lot of sunlight. It actually occurs all the time, but it's just not bright enough. You get a double reflection going on inside here. So this makes the primary rainbow, this makes the secondary rainbow. Notice the order of the colors in the secondary. Flipped. Cool that. Sometimes in winter and fall times you see rainbows near the sun. These are sundogs. They are due to refraction or dispersion, but it's different geometry because they're ice crystals rather than water. Cool. The worksheet I bumped to Friday. We'll do a lab tomorrow. Okay. So how many people are in A-Push? Okay, so watch